In this video, we're going to be talking about the importance of time when it comes to impulse. To do that, we're going to look at two examples. One in which we're trying to minimize the amount of time that a force is acting, and one in which we're trying to maximize the amount of time that the force is acting. We'll start with the case where we want to minimize it. We saw it just a moment ago. It's the so-called tablecloth trick. We did it with a piece of paper and a weight, but the idea is the same. I've drawn the basic setup here, though perhaps not particularly well. We have the table with the piece of paper and the weight sitting on top of it. Let's start by a brief refresher of how friction works. If two surfaces are in contact, they'll always be experiencing some amount of friction. The strength of this friction is related to two things. The first thing is called the coefficient of friction. The coefficient of friction is just a number that tells us how strong the frictional force is between two objects. It will almost always be a number between 0 and 1. Lower numbers correspond to weaker friction, and higher numbers correspond to stronger friction. The second thing that the force is related to is the so-called normal force between the objects. To see why the normal force is important, let's consider a very simple example. Our stick figure here is standing on the ground. What forces are acting on this stick figure? We know for sure that there's a gravitational force pulling down. But there has to be another force. If the only force acting on the stick figure was the gravitational force, then the stick figure would be accelerating downwards. But we know that's not the case. They're just standing there. So there must be another force in play. That force is called the normal force. It is a force between the ground and the stick figure, and it points up. The ground is supporting the stick figure so that they don't just fall to the center of the earth. How strong is the normal force? Well, it must be the same strength as gravity, just pointing in the opposite direction. If the forces were not balanced, then the stick figure would either fall through the ground or fly up into the air. And none of those things are happening. They're just standing there. It's the same exact thing here. The weight is pushing down on the paper because gravity is pulling on it. The paper has to push up on the weight because everything is just sitting there. It's not important that we know what the strength of this force is. It's just important that we know what's causing it. So the frictional force between the weight and the paper can be written like this. The frictional force is equal to the normal force with which the paper is pushing on the weight times the coefficient of friction for the weight and the paper. We want to know how much momentum is given to the weight by the paper as it moves. Well, we know that the change in momentum for an object is equal to the force on an object multiplied by the amount of time that the force is acting. In this case, the only force that is acting on the weight in the direction that we care about, which is left to right, is the force of friction between it and the paper. So the change in momentum for the weight is just this. This number, the force of friction between the objects, doesn't change because it's only related to how heavy this weight is and the properties of the paper and the weight's material. But this number can change depending on how quickly we pull the paper out from under the weight. If we do it very fast, in other words, if delta t is very small, then this delta p will also be very small, and the weight will only move a tiny bit. Whereas if we take our time, delta t will be very large, and so delta p will be very large as well. This corresponds to the case where the weight is given enough momentum that it just slides right off the table. But now let's look at an example where we might want to increase the amount of time that a force is acting over. The example we're about to do might seem a little morbid, but it's a good example of how understanding some basic physics can help make us much, much safer. Let's imagine a person in a car crash. We're going to see how adding an airbag to a car greatly improves the outcomes for people in car crashes. We're going to model our car crash like this. Let's suppose this driver is traveling this way at 30 meters per second when they run into a wall. The collision takes only about 0.05 seconds. In that amount of time, the driver goes from traveling 30 meters per second to traveling 0 meters per second. Let's calculate the force that the driver would feel. We know that the change in momentum of an object is equal to the impulse received by the object. So let's calculate the change in momentum for the driver. Their initial momentum is just 30 meters per second times 40 kilograms. And their final momentum is just 0. So their change in momentum is just negative 1200. If we set this equal to impulse and use the fact that the collision only takes 0.05 seconds, we can determine the force that the driver feels. So the force that the driver feels in this case is 24,000 newtons. That's a huge, huge force. But now let's imagine that we add an airbag to this car. By adding an airbag, we're causing the amount of time it takes for the driver to slow down to be increased. Instead of just running into the front of their car and stopping there, they run into this nice big pillow. This pillow slows them down more gradually. Let's say that now instead of taking 0.05 seconds to come to a stop, the driver takes 0.25 seconds to come to a stop, about 5 times longer. What is the force that the driver will feel? Well, the change in momentum is the same. They're still starting and ending at the same speed. But now in this equation, delta t is 5 times larger, which means the force will be 5 times smaller. So now, the force that the person will feel, instead of being 24,000 newtons, will only be 4,800 newtons. This is a huge reduction for a relatively simple safety feature. Again, it's not that the change in momentum is different in the second case. It's only the amount of time over which the change in momentum occurs. By increasing the amount of time over which the slowdown occurs, we're decreasing the force that the person actually feels. This is a great improvement for a relatively simple safety feature. The physics behind it is very simple, and this is one of the reasons why cars are required to have airbags.